Here we'll discuss about autoionization of water and pH and pOH. As we discussed before, water is an amphoteric substance, meaning it can be a base or an acid. In this reaction, it acts as a base because it is the one accepting the proton from HCl. In this reaction, it acts as an acid because it's the one donating the proton towards NH3. Water molecules can also react with each other to form hydronium ion. We call this process, hydronium then hydroxide ions. We call this process as autoionization. So the word auto means self. So it's self because it's the same water molecules reacting with each other. And then we have ionization because from their reaction they form ions. Again, that's the hydronium then the hydroxide ions in this reaction. Let's determine the equilibrium expression for this reaction because here we'll determine the acidity of a substance based on the concentration of the hydronium. Then we have the hydroxide ions. That's equal to K is equal to the concentration of the products. That's equal to the concentration of H3O plus. Again, this one is the hydronium ion raised to the power of 1. Then we have the times the molar concentration of OH minus, also raised to the power of 1. That's over the molar concentration of the reactants. But here, our reactants are liquids, and again, pure liquids and solids are not included in the equilibrium expression. So this one is the equilibrium expression for this reaction. We also give this one a special name because it's an important constant in acids and bases. So that's Kw. So this W here means water. So this is the water ionization constant. That's equal to, again, the molar concentration of the hydronium ion times the molar concentration of OH minus. And we have determined the value of Kw. Kw is equal to 1.00 times 10 to the power of negative 14. Again, Kw is equal to the product of the concentration of hydronium and then the hydroxide ion. If we have the Kw, then we can actually calculate the concentration of either the hydronium or the hydroxide ions if one is given. Let's see how this works in this sample problem. Here, let's calculate the hydronium ion concentration of a solution in which the hydroxide ion concentration is 6.15 times 10 to the power of negative 2 molars. Let's write the given first. So here we have the given is the hydroxide ion concentration. So the hydroxide, that's the hydrogen and oxygen, that's the OH. So here the concentration of OH minus is equal to 6.15 times 10 to the power of negative 2 molar. And again, for this one, we can use the Kw. So that's Kw is equal to the molar concentration of the hydronium times the molar concentration of the hydroxide ion. Let's write this one here. So Kw is equal to the molar concentration of the hydronium ion, hydronium, that's H3O plus, times the molar concentration of OH minus. Now, of course, Kw is constant. It's equal to 1.00 times 10 to the power of negative 14. So we can use this value here, 1.00 times 10 to the power of negative 14. It's equal to the molar concentration of the hydronium, and of course we are finding this one, but we have the value of the OH. So that's the concentration of OH is equal to 6.15 times 10 to the power of negative 2. And of course we are finding for the molar concentration of H3O plus, or the hydronium ion. To find the value of this one, what should we do? So it's so simple, just divide both sides by this one, 6.15 times 10 to the power of negative 2. 6.15 times 10 to the power of negative 2. Then of course we can cancel this one. What's left on this side is this one. Okay, then to find out the value for this, simply divide this one. Let's first open our calculator. So if you have this type of calculator in your phone, so we have this 1.00. So for this one times 10 to the power of negative 14, we press this one. That's 1.00 times 10 to the power of negative 14 divided by 6.15, 6.15, sorry, 6.15 times 10 to the power of negative 2, and that's equal to this number 1.63 times 10 to the power of negative 13. That's 1.63 times 10 to the power of negative 13. I'll just flip this one para organize. We have the concentration of hydronium ion is equal to 1.60, sorry, 3 times 10 to the power of negative 13 molar. So this is the answer for this item. Let's have another one. Okay, first let's identify whether this one is acidic, neutral, or basic. It's acidic when the concentration of the hydronium is greater than the concentration of the hydroxide ion. It's neutral if it's equal, and then it's basic if the concentration of the hydroxide is greater than that of the hydronium ion. So here let's compare our uh, again, this one is our hydroxide, 6.15 times 10 to the power of negative 2, while our hydronium is 1.63 times 10 to the power of negative 13. These are scientific notations, so it's not obviously based on this number lang. It's also based on this one because, of course, these are very small numbers. So which do you think is much larger here? This number or this number? Of course, this one is negative, meaning it's less than 0, or we shift to the left. So let's try to expand this one. We have 6.15. 6.15 times 10 to the power of negative 2. So negative 2, we move 2 places here. So this one is equal to 0.0615 molar. How about for the hydronium ion here? Our hydronium here is 1.63. 1.63 times 10 to the power of negative 13. So we need to move 13 places. So 1, 2, 3, 4, 5, 6, and so on. I don't want to continue, but it's very obvious. Blah blah blah. Okay, so it's very obvious that here our concentration of the hydronium is larger than that of our hydronium ion. So we have the hydroxide is much larger. So this one is a basic solution. So diba, of course, when we go back, so it's an acid pag mas malaki yung hydronium, then pag mas malaki yung hydroxide, then it's basic. So in this case, since we have a larger hydroxide ion concentration, then this one is a basic solution. Next, we have this one. Calculate the hydroxide concentration of a solution in which the hydronium ion concentration is 2.65 times 10 to the power of negative 3 molars. So let's write the given first. The given here is this one. We have the hydronium ion concentration. So for the hydronium, that's H3O, diba? Okay, then it's equal to 2.65 times 10 to the power of negative 3 molar. And then here we are asked to find out the molar concentration of the hydroxide. That's the OH minus. That's to be found. Okay, so let's use the Kw equation. The Kw is equal to the molar concentration of the hydronium ion times the molar concentration of the hydroxide ion. Of course, Kw is it's constant. It's always equal to 1.00 times 10 to the power of negative 14. Then how about the hydronium ion? It's given here 2.65 times 10 to the power of negative 3. And then we are finding out the value for the concentration of the OH minus. So again, this bracket here, this one is read as the concentration of the substance inside this bracket. So to find out for the concentration of OH minus, just divide both sides by 2.65. 2.65 times 10 to the power of negative 3. 2.65 times 10 to the power of negative 3. Of course, we can cancel this one. What's left here is the OH minus. I'm just going to flip this one for organization. Then we divide this one 1.00 divided by this one. Let's use our calculator. 1.00 times 10 to the power of negative 14 divided by 2.65 times 10 to the power of negative 3 is equal to 3.77. 3.77 times 10 to the power of, I lost it, negative 12. Negative 12 molar. Next, let's identify whether this one is an acid or a base. So let's compare our hydronium. Then we have the hydroxide concentration. Again, it's acidic when the hydronium is greater than the hydroxide. Then we have it's basic if the hydroxide concentration is greater than that of the hydronium concentration. So we have here 2.65 times 10 to the power of negative 3, 3.77 times 10 to the power of negative 12. So again here it's based on the exponent. So this is negative 3, this one is negative 12. And of course this is a negative, so meaning this one is much smaller compared to this one. So in this case the hydronium concentration is greater than that of the hydroxide concentration. Again, it's much bigger because it has a lesser negative na exponent compared to this one. So this one is an acidic solution. Okay, so of course we measure the acidity of a substance. So that's actually based on the concentration of the hydronium ion or the hydrogen ions. Again, it's still the same, diba? So it's just the same concept. So it's neutral when the hydronium concentration is equal to 1.0 times 10 to the power of negative 7. It's when it's less than this value, it's acidic. Then if it's greater than this value, that's basic.